let's talk now about the idea of calculating sample sizes, specifically for inferences regarding the mean. Now, what we want to do is set this up the same way as we did when we looked at sample sizes for proportions. What we did is took the margin of error and set it equal to the way we define the margin of error or calculate the margin of error in the confidence interval. Now, when we do this and solve for n, what we end up with is n is equal to t on the appropriate degrees of freedom of alpha over 2 times s divided by the margin of error that we specify, this whole quantity squared. So this looks like it should be what we will use for our sample calculations, or our sample size calculations. However, there is an issue with it. And that issue is simply two things. First of all, the t, because t actually depends on and the sample size. So in order to find the proper t, you have to have the sample size, because t, on the appropriate degrees of freedom, as you recall, is a family of curves. As n changes, n minus 1, the degrees of freedom, also change, and so does the curve. So you need to know n before you can find t. So it's that chicken or the egg sort of an argument once again. So what we're going to do instead is we will simply use z. We will use the value of z, alpha over 2, to calculate the sample size needed to go off and take your sample. Now, as you know, the t distribution and the z distribution converge very, very quickly. So using a z is not that much different from a t. And keep in mind that although the mathematics is absolutely dead on, 100% exact, the application is not. So using a z is really not a big deal here. Now, the other issue is s. S depends on the sample, because it is the sample standard deviation. That's what it is. So that's another problem. We can't have the sample standard deviation before we have the sample. So what we're going to do is come up with a way to estimate s, a reasonable approximation for s, to get us going so we have a good idea of what sample size we should be using. Now, the way we're going to do that is think about the normal curve for a moment. The mean, if I go out 1 standard deviation, 2 standard deviations, both directions, I have 95% of my data should be in there. 95% of the population should be in there if this is a normal curve. Anything beyond 95%, that last 5%, 2.5 in each tail, we start thinking as being unusual observations. So, if I can get an estimate for what I think the high value is going to be when I collect my data, that should be around 2 standard deviations away. Maybe a little bit more, but somewhere in that area. The low estimate should be around 2 standard deviations below. So if I take a look at the high estimate, subtract it from the low estimate, and divide it by 4, because here's 1, 2, 3, 4. This total distance is actually 4 standard deviations. This should give me a pretty good estimate for what sigma is, which we can use in here. So what we need to do is have a way to come up with that high and the low, which sometimes is more of a guess than anything else. If you're acting as a consultant, you can ask your client, what do you think the high and low values are, and do this calculation. And make it clear to your client that the sample size calculation is very, very sensitive to these high and low values. Another possibility is to estimate the best you can what you think high and low is going to be, calculate this approximation out for a sigma, find the sample size, and let's just say the sample size turns out to be like 67 or something. Well, go out and take a sample of 25 or 30. From that sample, if it's reasonably representative of the population, if you calculate the sample standard deviation, then you have a reasonable estimate for what sigma should be. Compare it to your high-low subtraction over 4 estimate. And maybe redo the sample size calculation based on using the sample standard deviation from that smaller sample. Now, once you do that, maybe it says, well, you need 42 rather than the original 67 or whatever it was. Well, go out and get 42, and now you're in the ballpark. You've got a decent sample, so you can go ahead and work with it. Okay, let's go ahead and take a look at an example here and work through this thing. Now, suppose you're about to conduct research to determine the average time it takes for a pain reliever to take effect. The doctor wants to be certain within 3 minutes. This is kind of important. The 3 minutes, that's the margin of error. And 98% certainty. That's going to dictate what alpha over 2 is going to be. What sample size is needed? Well, we need more information. So suppose we go to the doctor and say, what do you think the high is going to be? And he says, you know, I really believe, to the best of my ability, that the longest it will take is about 47 minutes. And the quickest or the lowest is probably going to be around 12. I can't imagine it happening faster than 12 or longer than 47. So say, all right, so I'm thinking a reasonable estimate for sigma is going to be about 47 minus 12 over 4, which is 8.75. So now I have this, and I can go ahead and calculate my sample size. So the sample size is going to be, I need to find z of alpha over 2, and then I'm going to use 8.75 as my estimate for sigma, and 3 is the standard deviation, the margin of error, and square it, and that will give me n. And I can get z of alpha over 2 because if we want to be 98% certain, that means that alpha equals 0.02, so z of 0.01, that's 0.02 over 2, equals, and you can get that using inverse norm. That should be an R, sorry about that. You can get that using inverse norm of your calculator. Simply substitute that number and calculate it out. But what I'm going to do instead is I'm going to go ahead and jump to my calculator. And I'm going to go to Program. And I'm going to look for the sample size program down here. And it's actually called Sample SZ because there's not enough room in the calculator to put the full sample size as a name. Select it for hitting Enter. Hit Enter again to actually run the program. Tell it, yeah, I want to do this for the mean. And now answer the questions. Well, my estimate is 8.75 for the standard deviation. So type that in, hit Enter. The margin of error, doctor said you want to be within 3 minutes. That's plus or minus 3. Confidence level, well, that was 0.98. Hit Enter. It's telling me I need 46.039. Now, obviously, if there's anything other than zeros to the right of the decimal, I'm going to go up. So I'm going to tell the doctor that he needed a sample of 47. And this is where I'm going to start at. I may do the iterative process, I may not. It depends totally on the situation I'm actually working with. But basically, that's it. That's really all you need to do to calculate the sample size that you need if you're going to go out and take a survey or collect some data with the idea of doing inference for the mean.